Okay, hello everybody. Welcome to a very special talk by Rajat Gupta. So, Rajat is one of the reasons, many reasons why we started this seminar. He's hang on.
I'm not able to hear.
Hang on. There's something wrong.
Let me also see if my charger. Oh, yes. Wait.
I'm hearing two slides. So, okay, let me. Uh,
Because my charging was not working. Yeah, it's working now.
uh, uh, Okay, sorry about that. Hello and welcome again. It's a real pleasure to introduce Rajat Gupta. He is one of the reasons why we began this seminar series in the first place. He is one of the first few PhD students in this group who is about to graduate. He's just about to submit his thesis in IIT Gandhinagar, and following which he will continue as a postdoc in IIT Gandhinagar. And this is just chapter one. Whatever he's going to present today is just the chapter one of his thesis. I should mention his thesis is under the direction of Atul Dikshit, who is one of the co-organizers. Okay, Rajat, go ahead.
Thank you for the nice introduction. So, good afternoon, everyone. So, first, I want to thank the organizers for inviting me to present my work on this special function and number theory seminar. So, today I'll be talking to you about the Koshlikov zeta function and modular relations. And this is a joint work with Professor Dikshit, which we have just submitted for the publication. And it's a part of my thesis. So let me go over the table of contents. First, we tell a story about how Professor Dikshit actually discovered this Koshlikov manuscript. Then we go over the origin and content of this manuscript. Then we talk about how this theory of Koshlikov zeta function appears. And then we go over the new results which we obtained in this theory. And I'll end the talk with the possible future problems in this direction. So Ramanujan, in his last day of his life, actually wrote a 130-page long manuscript, which is considered to be a mathematical equivalent to the discovery of Beethoven's 10th Symphony. And it was discovered by Professor George Andrews in 1976 in the Trinity College Library. It has many advances in many fields of mathematics, like outside the number theory and analysis too. Like the Mach theta function, this Mach theta function actually appears in various branches of physics, like black hole theory and string theory. So the story starts here from 2010, where Professor Dikshit actually working on his PhD thesis. He came across a survey article which was written on the account of the birth centenary of Nikolai Sergeyevich Koshlikov, which was a Russian mathematician. So here's the picture of Koshlikov while giving a PD class to his students. So he was an outstanding mathematician who made a seminal contribution to number theory as well in the differential equation. So since the article contains a very brief introduction about the work of Koshlikov in mathematics, so Professor Dikshit actually decided to collect all the possible work which was published by Koshlikov at the time. Unfortunately, there was no overlap between what he was doing in his thesis and what Koshlikov had done. But there was a very interesting piece of information in that survey article, which we will just read here, that the repression of the 30s, which affected scholars in Leningrad, continued even after the outbreak of the Second World War. In the winter of 1942, at the height of the blockade of Leningrad, Koshlikov, along with the group of scientists, was actually arrested on fabricated dossiers and condemned to 10-year correctional hard labor. So after the verdict, he was exiled to one of the camps in Urals. So Urals are the mountains. So on the grounds of complete exhaustion and complicated pellagra, Koshlikov was classified in the camp as an invalid and was not sent to do any usual jobs. On a very serious shortage of paper, he was forced to carry out the calculations on a piece of plywood, periodically scraping off what he had written with a piece of glass. Instead of that, in 1943 and 1944, Koshlikov actually wrote two long memoirs. So this is what written in not in Russian but in English. In that, so it translates like a study of some questions in the analytic theory of rational and quadratic field. This is the first manuscript, and in the second manuscript, a study of class of transcendental functional equation defined by the generalized Riemann equation. So the first manuscript, which was lost in transit from jail to mathematical community, actually lost. But we think that after releasing from jail, Koslov actually reproduced this work in these three papers, which is cited here. And the second manuscript, a study of class of transcendental functions defined by the generalized Riemann equation, is a subject of this talk. And this and Vinogradov and Bernstein and UV Lenig actually was so impressed by the content of this manuscript that they immediately recommended for its publication, but with a different name. Like it was published by the name of N.S. Sergey, not N.S. Koshlikov. So the next big task was to try to obtain the copy of that manuscript. So it was not hard for him, not hard for Professor Dixit, because he was there at the UIUC. So the librarian Tim Cole actually told him that the CRL actually had a copy of it. So, and CRL actually was very kind enough, and they scanned the whole 150-page Russian manuscript and emailed it to Professor Dixit. So this is the first page of the manuscript. So even though this manuscript was published in 1949, but we think that the Koshlikov had this idea about the concept of this manuscript from the mid 1930s, because he wrote two papers in 1923 and 1935, cited below, which actually follows the same concept as appear in manuscript. So we think that he has the idea about the concept of this manuscript from 1930s, from these two papers. So the genesis of this manuscript is a problem coming from physics, which arising in the heat distribution. So let me state the problem. So consider a sphere of radius R2, and suppose that the radiation occurs on its surface with radius R equal to R2, and with a medium at zero temperature, and assume that the initial temperature of the surface is zero, and the heat source which are placed on the spherical surface of radius R1, and further assume that the rate per unit time of heat propagation from the whole surface is Q, then the problem actually concerned with finding the temperature of the sphere at time t equal to 0. So this boils down to this PD, where K, H, and rho are defined by these specific constants. So K is thermal conductivity, H is emissivity of the surface, and C and rho is the density of the material forming of the sphere. Then this is the PD, which takes form. And if you apply the method of separation of variable, then we find out that the solution of this PD actually depends on the solution of this characteristic equation, mu cos mu plus p sin mu equal to 0, where p is equal to R2H minus 1 and mu is its eigenvalue. This is coming from these boundary value conditions. Like if you take like mu square, like del uv by del t is equal to a square del 2v upon del R2 is equal to mu square, then if you solve this PD by separation of variable, you will find out that you need to satisfy this function, like this characteristic equation, like mu cos mu plus p sin mu equal to 0. Now, so this characteristic equation actually forms the crux of this Koshlikov theory of zeta functions. So let me start with the basics. So before going over the basics, let me tell a story that this project was given by Professor Dixit just last year. And the big task was to first translate this 150-page long manuscript, which was in Russian to English. And so first we have to translate that manuscript, and then we have to study it, and then we have to find some new results on it. So it was a very nice experience for both of us. And so we begin with giving the basic facts about the Riemann zeta function. So the Riemann zeta function for real part of is defined by this absolutely convergent series, which is for real part of s greater than 1. So it can be analytically continued to the entire complex plane except for a pole at s equal to 1. It also satisfies the following functional relation. And you can always write it in an asymmetric form, which is given by this, that's zeta 1 minus s 2 pi to the minus s gamma zeta s cos pi s by 2. And you can easily deduce it from here. You just take all the stuff from here in the right and in the left hand side and use the reflection formulas of gamma function, and you will obtain this relation. Now, Hamburger actually gave a theorem, and in the theorem he showed that the Riemann zeta function actually can be characterized by its functional equation. So he showed that if you have two series f and g, which are absolutely convergent for real part of S, and f is a meromorphic function of finite order with finitely many poles satisfying this functional equation, then f and g has to be constant multiple of Riemann zeta function. And here's a picture of Hamburger. And in the series of paper from 1920 to 22, he actually considered a asymmetric form of this functional equation, that f of 1 minus s is equal to 2 cos pi s by 2 gamma s upon 2 pi to the s and gs, where he specifically considered that f is a Dirichlet series where g is not in general a Dirichlet series. While in the previous case, both the series were Dirichlet. Both the series are Dirichlet series, like f and g both are Dirichlet series. But in this part, he considered f as a Dirichlet series, but g is not a Dirichlet series. So, but he studied the properties of these f and g satisfied by this functional equation, but he did not give any such example of f and g. Now we move to the Hurwitz formula, where if you tweak a Hurwitz formula of by a little, then if we find out that for real part of s greater than 1 and a between this strip, that a is between 0 and less than equal to 1 is given by this. Now from here you can see that this zeta 1 minus s comma a is nothing but is defined by this Hurwitz zeta function. So it's a Dirichlet series, while this part is not a Dirichlet series. So this can be an example of that functional equation. But here is the reason why it's not a complete example, because this is only true for real part of s greater than 1. So the explicit example of this pair of Hamburger's theory was given by Koshlikov in his manuscript. So he started the manuscript by giving the example by giving such pair which satisfies the Hamburger's theory. So these are the two zeta functions. So and these are aforementioned pair f and g. So f is defined by zeta p of s, which is a Dirichlet series, and eta p of s, which is not in general Dirichlet series, because here you can see this constant is dependent on s. So zeta p is defined by this Dirichlet series, which is absolutely convergent for real part of s greater than 1. And here I want to mention a fact which we'll see in later, that if you take p tends to infinity, and in that characteristic equation, the root lambda j actually goes to j integer, and if you take p tends to 0, that lambda j goes to j minus half for every j. So if you apply that fact here and you take a modulus, you will find out that zeta p is absolutely convergent for real part of s greater than 1. And similarly, eta p is also absolutely convergent for real part of s greater than 1, where this constant s comma 2 pi p k sub k is defined by this integral representation. And as I said, these lambda j's are increasing sequence of positive real roots of this characteristic equation. And if you take p tends to infinity, lambda j goes to j, and if you take p tends to 0, lambda j goes to j minus half. And we can easily derive it from here. You have to just take p from here and there in the case of p tends to infinity and p tends to 0 simultaneously. Thus, at p tends to infinity, that zeta p of s reduces to zeta of s, and eta p of s also reduces to zeta of s. While in the case, if we take p tends to 0, zeta ps actually reduces to 2 to the s minus 1 times zeta s, and eta ps reduces to 2 to the 1 minus s minus 1 times zeta of s. So Koshlikov showed that these two zeta functions, zeta p and eta p, actually can be analytically continued in the entire complex plane as similar to the Riemann zeta function. And also it has a pole at s equal to 1 with residue 1, and zeta ps has residue 1 at pole s equal to 1, and eta ps also has residue 1 upon 1 plus 1 upon pi p at s equal to 1. So as you can see, if you take p tends to infinity, this will reduces to 1, and eta ps also reduces to 1, reduces to Riemann zeta function. They also satisfy the following functional equation: zeta p of 1 minus s is equal to 2 cos pi s by 2 gamma s upon 2 pi to the s, and eta p to the s. So now, with the above setup, he also developed the function associated to those Riemann, the function associated to these Koshlikov zeta function. Like he introduced the generalized gamma functions, which he called the gamma morphic function of first kind and second kind, the generalized Euler constant CP1 and CP2, generalized Bernoulli polynomial, generalized theta function, generalized Hurwitz zeta function, and many more. And that manuscript also contains the generalized Poisson summation formula and generalized Abel-Plana formula. So as we know, zeta p of s has a simple pole at s equal to 1. So it can be expanded through Lorentz series expansion. So zeta p of s equal to 1 upon s minus 1 plus cp of 1 and then error term with s minus 1. So as you take, so if you take zeta p of s minus 1 upon s minus 1 and you take limit s tends to 1, you will find out that the limit will be cp of 1. And if you take p tends to infinity, this will reduces to Riemann zeta function, and the cp1 reduces to the Euler constant. And the cp1 is defined by this limit, where the cp1 is defined by this limit, where the limit is over summation j equal to n minus 1 with this term minus log lambda of n. Now again, if you take p tends to infinity, so you can see here that this thing reduces to 1, and as I mentioned that lambda j goes to j as p tends to infinity. So this will reduce to the limit definition of Euler gamma constant. Similarly, eta p also has a simple pole at s equal to 1 with this following Lorentz expansion, where the constant term now is cp of 2 minus this, where cp of 2 is given by this limit and q mu is nothing but incomplete gamma function. We're defined by this. So if you take p tends to infinity, this thing goes to 0, and this limit will reduces to the limit of limit definition of Euler gamma constant. Now let me move to the gamma morphic function of the first kind. So it is defined by this product. So it's little bit it's look familiar with the product definition of gamma function. So Koshlikov defined this and defined this by gamma 1 of p of x. If you take p tends to infinity, this gamma 1 of p and cp1 reduces to gamma function and Euler gamma constant. Now if you take log on both sides and differentiate with respect to x, then you will get a generalization of digamma function, which we defined it by psi 1 of p comma x, and it has a following series representation. It is due to Koshlikov. From here you can see that it has a pole at x equal to 0, at pole at x equal to minus lambda j, as well as it has a pole at x equal to infinity. Koshlikov not only gave the series representation of it, but he also obtained an integral representation of this psi 1 of p of x, which is very useful, which is very useful in the coming slide, where I1 of x is given by this integral representation, where sigma of t is nothing but p plus t upon p minus t. So as you see, if you take p tends to infinity, it will reduces to 1, and if you take p tends to 0, it will reduces to minus 1. Similarly, gamma morphic function of second kind is defined by this representation, where d of s is nothing but derivative with respect to x. It looks a little bit complicated, but its properties are very natural and very elegant. So if you take p tends to infinity in the above form, then gamma 2 also reduces to gamma of n, and cp2 also reduces to Euler gamma constant. It also has an analogous theory. It also has a generalized digamma function, which has a series representation like this with the same property that it has pole at x equal to 0 and x equal to minus k. It also has an integral representation where I1 star x is actually defined by this, and this new thing which is defined here is that cp of t is defined by this series. And from here you can see that if you take p tends to infinity, then this thing will reduces to 1, and this is nothing but geometric series running summing e to the minus jt, because lambda j goes to j, and that will reduces to 1 upon e to the t minus 1. Now back to the functional equation. So functional equation, they were satisfied by zeta p and eta p is given by this. So the natural question came into our mind is that is there any symmetric form of this function, symmetric form of the functional equation satisfied by eta p and zeta p? So the question is yes. So for that, we first define omega p of s by zeta p of s plus eta p s upon 2. And if you play with these two equations, then you find out that it satisfies the following elegant looking functional equation, that that it is almost similar to the Riemann zeta function, but in the place of Riemann zeta function, now we have omega p of s. And why it is not equal to, why it won't be equal to constant times zeta of s according to the Hamburger's theory? Because omega p of s is not a Dirichlet series, because Eta PS is a Dirichlet series and eta P is not in general. So that's why omega P is not a Dirichlet series. So it won't be the constant time of Riemann zeta function. So it's easy to see that if you take P tends to infinity, that omega Ps reduces to Riemann zeta function. And in the case of P tends to 0, this omega P of S reduces to 2 to the S minus 1 plus 2 to the minus S minus 1 Riemann zeta function. As you can see, this is invariant under S goes to 1 minus S. So it won't give you the new functional equation for Riemann zeta function. It will get cancelled out on the both sides if you take P tends to 0. Now, let's discuss about the modular relation which was given by Ramanujan. So before stating the modular relation, let me first define two Riemann's function, Riemann psi and Riemann c function. Riemann psi function is defined by pi to the minus s by 2. So s minus 1 upon 2, gamma s by 2 and zeta s. So you can see this is the multiple of s minus half upon 2 of the left hand side of the functional equation of Riemann zeta function, where Riemann c function is defined by Riemann psi half plus it. And then Ramanujan consider that if you take AB equal to pi, then the following modular relation holds. And before going to next slide, let me say that in the Koslakov manuscript, actually Koslakov actually gave a last chapter of his manuscript completely devoted to the theory of Ramanujan, theory which was given by Ramanujan, like modular relations. So in the 9th chapter, he actually defined two functions analogous to the Riemann's function. So the Koslakov function defined by Riemann psi p of Koslakov psi p of s is defined by pi to the minus s by 2, ss minus 1 by 2, gamma s by 2, and omega p of s. Similarly, the left hand side of the functional equation satisfied by omega p of s, multiply with this, and analogously Riemann c function, Koslakov c function at the base p. And he obtained for AB equal to pi, he has the following function, he has the following modular relation, similar to what Ramanujan had, and it is actually the generalization of the previous one. So as you can see, it can be easily verified if you take P tends to infinity in this modular relation. These two terms will reduce to 1 upon e to the 2 pi x minus 1, multiply with 2, and this again we obtain 2 upon 2 pi x. So you take 2 common from both the sides, so you will have the Ramanujan's formula. Now let me move to the another interesting formula for Ramanujan, which can be found on the in the page 220 in his lost notebook. So before stating that, let me first define the digamma function or logarithmic derivative of gamma function, which is defined by gamma prime x upon gamma of x, and define phi x is equal to psi x plus 1 upon 2x minus log x. So this term will coming from the expansion of psi x at x into infinity. So the first two terms in the expansion of psi of x at x into infinity are log x and 1 upon 2x. So we subtracted those first two terms from psi of x to get the absolute convergence, which we'll see in the next slide. So he obtained that if we take alpha beta are two positive numbers such that alpha beta equal to 1, then the following modular relation hold. So here we use the absolute. So to prove the absolute convergence, we need to expand the psi of x at x into infinity. As I said, these two are the first two terms. So the third term will be of the order of 1 upon x square. So this will be an absolutely convergent series. So the left hand side is completely defined. So this is what modular relation given by Ramanujan. So the natural question came to us was, can we obtain an analogous formula in this setting, in the Koslakov zeta function setting? And the answer is yes. So before going to state it, let me first define some important functions. So capital phi of p of x is defined by phi 1 of p of x plus phi 2 of p of x, where phi 1 of p is defined by this and phi 2 of p is defined by this. And recall the extended Euler constant given by this limit, the CP1 and CP2. Koslakov not only gave this limit representation of it, but he also gave the integral representation of it in the manuscript. But for our purpose, we need a new representation of CP2, which we derive in our paper and given in this lemma, that CPU of 2 is 0 to infinity with this representation. And this can be easily reduced from Frolani's representation of log of x, because because in course of proving this CP2, you need a formula for log of x, because here you can see the log n is present. So that integral represent actually coming from here. So this is our main theorem, which is state if alpha beta are two positive numbers such that alpha beta equal to 1, then this modular relation hold. So let me comment on this formula that when we started to prove this formula, we don't know anything about from where to start. Like we don't know anything what will be the left hand side, what will be the right hand side. But when we started from the right hand side, we think that as in the case in the Ramanujan, we have Riemann c square t by 2. So we were thinking that we may need Riemann c p square t by 2. That means we started with here Riemann c p square t by 2, but that's not the case, as you can see here. So we started from the left hand side, and we showed that this left hand side is equal to some integral representation, and that integral representation is nothing but this. So let me give a brief sketch of the proof. And as p tends to infinity, the above formula reduces to the Ramanujan's transformation. So we first show the absolute and uniform convergence of this series, where phi1 and phi2p is defined by this. So what we do is that we first convert phi1 and phi2p from here in the integral representation. So we gave an integral representation of phi1 and phi2 with the help of the integral representation of psi1 of p, where I1 is defined by this and sigma t is defined by p plus t upon p minus t. And we have phi1 of phi1 comma p of x is nothing but minus of this integral. So now we have phi1p in this form, and now we have an integral representation of it. And now you have to sum it, right? So for that, let me first estimate phi1 of p as x tends to infinity, and it is by using the elementary facts we find that phi1 of p can be bounded by 1 upon 12 x square. And if you sum over n, and in the place of x, if you take n, then it is nothing but it is less than equal to the sum which is running over n with 1 upon n square, which is an absolutely convergent series, which proves the absolute convergence of this series. And similarly, one can also prove same for phi2 of p, which is given by this bond. So phi2 of p is given by this bond, and from here, if you take a summation on both sides, you will see that phi2 of p is absolutely convergent series. Now we sum phi1 of p of n of alpha, and sum is running over n, and we convert this series again into the integration by using the following fact, this one. And we find that this series n equal to 1 to infinity phi1 of p and alpha can be represented by this integral. And now what we use that we use Frulani's formula to write log 2 pi of a in this form, and use our new representation CP2 with log 2 pi alpha to get the following representation. And once we get that, we use 3 and 4. We add actually 3 and 4 and multiply with root alpha in such a way that this form has a following integral representation. As you can see here, phi2 comma p is missing. So similarly, one can also apply the same theory to get the following representation for analogous representation for phi2 of p, which involves cp of 1 minus log 2 pi alpha upon 2 alpha and has the following integral representation. Now the remaining thing is to add these two representations for this one, equation 5, and this equation. So once you add it, you will boil down to this integral representation on the right hand side. We break this representation into two parts. The first part is HP of alpha, and the second part is constant multiple of G of alpha. And next we show that this G of alpha is identically equal to 0 by using the result of Bernd and Dixit. And we show that this HP of alpha is nothing but the integration which we saw in the theorem, in the main theorem, the theorem which involves the integral representation which involves the Riemann-Z function and Koslakov-C function. So we use the result of Bernd and Dixit, which shows that G of alpha equal to 0, and our result, which shows that this integral is nothing but this one, with n equal to 1 by 2 log alpha. And combining with this fact, we derive that this left-hand side of the main theorem, that means root of alpha Cp of 1 plus Cp of 2 with this term plus this series is this one, is this integral. Now, as you can see, if alpha goes to 1 by alpha, so this integration is invariant under that operation. That means if you take alpha equal to 1 by alpha, that won't change, because cos of minus 1 upon t log alpha is again will be cos of t by 2 log alpha. So this will be invariant under alpha goes to 1 by alpha. Thus, if we impose the condition alpha beta equal to 1, then we obtain the following modular relation. So this completes the proof. Now, what happens if you take p tends to...
You replace alpha by beta. That's what you're trying to say. Not
Yeah. We replace alpha by beta by imposing this condition, because alpha beta equal to 1, that is nothing but alpha goes to 1 by alpha, if you see. Yeah, thank you. Now we consider the case p tends to 0. So as we have seen in the case of, if we take p tends to infinity, we obtain the Ramanujan's formula. But what happens if we take p tends to 0? So we use that the lambda j's are the positive real sequence, increasing sequence of positive real roots of this characteristic equation. And as we saw that p tends to 0, lambda j goes to j minus half. And if we employed this fact in the previous theorem, then if we consider tau of x in this by this combination of digamma function, we find that for alpha beta equal to 1, we have this modular relation. Now let move to the second part of this. Let me move to the second part of this work, which is on the special values of these Koch-Lagrange zeta function, like odd values, like Koch-Lagrange zeta functions at odd arguments. So before stating that, let me go over the Ramanujan's formula for zeta p of 2m plus 1. So for m belongs to z and real part of alpha, real part of beta positive, such that alpha beta equal to pi square, we have such modular relation. So Koch-Lagrange in his manuscript defined two functions, sigma p of t by this series and this function 1 upon sigma t upon 2 pi e to the t minus 1. And if you take p tends to infinity, both reduces to 1 upon e to the t minus 1. As you can see, this 1 upon e to the t minus 1 actually appears here. That means if we have the formula for analogous formula for Koch-Lagrange zeta function, that means if you take p tends to infinity, we will get this formula. But what happens if we take p tends to 0? So if we take p tends to 0, these two functions will reduces to different functions, like sigma p of t reduces to 1 upon e to the t by 2 minus e to the minus t by 2, where you can write this in the sine hyperbolic form. And this function reduces to minus 1 upon e to the t plus 1, where sigma t is given by p plus t upon p minus t. So this is the second main theorem of this talk. So for m belongs to z and real part of alpha and real part of beta positive, and if we impose the condition alpha beta equal to pi square, we have the following modular relation. As you can see, it appears the Koch-Lagrange zeta function, first Koch-Lagrange zeta function, which is zeta p, and where B2JP is nothing but the generalized Bernoulli number defined by Koch-Lagrange by this integral representation, and sigma p of z is defined by this series. As you can see, if we take p tends to infinity, this will reduces to 1 upon e to the t minus 1, and if we take p tends to 0, it will reduces to sine hyperbolic functions. Now, in the case of p tends to infinity, it is clear that it reduces to the Ramanujan's formula for zeta p to m plus 1. But for p tends to 0, and we know that lambda j goes to j minus half, so we obtained the formula for Hurwitz zeta function at a equal to half. So we have this formula for alpha beta equal to pi square. We have this modular relation. Now, since both the formulas are true for m not equal to 0, so let me give a formula for m equal to 0 case. So which is nothing but a p analog of a transformation formula for logarithmic derivative of static and eta function. So for alpha beta equal to pi square, we obtain this relation. And if you take p tends to infinity, we get the corollary of Ramanujan's formula for zeta to m plus 1 given by Ramanujan itself. And if you take p tends to 0, we obtain new modular relation for alpha beta equal to pi square, which satisfy this modular relation. And here we use the fact that lambda j goes to j minus half as p tends to 0 in the above formula. Now, what happened? Now, what if we consider the case m less than minus 1? So what we do is that we replace m by minus m minus 1 in our main theorem. Then for m greater than or equal to 1 and alpha beta equal to pi square, we obtain this modular relation where we don't have any Bernoulli sum or any finite sum. So it's a complete modular relation. Hence, if we take alpha beta equal to pi and m an even integer, then surprisingly, we obtained a closed form of this equation, closed form of this series, which is equivalent to minus zeta p minus 2m minus 1 upon 2. And as p tends to infinity, it reduces to the known formula. And if you take p tends to 0, we obtain this new formula where sum is j1 to infinity, where now the argument is 2j minus 1. That means odd number, you are summing over odd numbers, 2j minus 1, 2m plus 1, e to the pi 2j minus 1 plus 1 is equivalent to this form, where b is nothing but the Bernoulli numbers. Now, if we take m equal to minus 1 case, that in the remaining case of the previous theorem, then for alpha beta equal to pi square, we have this representation. And if you take alpha, again, if you take alpha beta equal to pi, then you have following representation. And if you take p tends to infinity, then we get the closed form of such series, which is very well known, that j equal to 1 to infinity, j upon e to the 2 pi j minus 1 is equal to 1 upon 24 minus 1 upon 8 pi. And from here, we can conclude that this series is transcendental because this is rational and this pi is transcendental number. But if you take p tends to 0 in above case, then you find out that if you sum on the odd arguments of such this series, you will have, then you will get the equivalent, then this series will equal to 1 upon 24, which is a rational number. So this series are rational quantity. Now, the second main theorem, now we repeat the main theorem to conclude the other corollaries of this. So this is the main theorem. Now, to obtain the Lurch formula for zeta 4m plus 3, we put alpha beta equal to pi and m as 2m plus 1. That means odd positive integer. Then we have this formula, zeta 4m plus 3 plus 2, and this series. And this is a pi multiple of this finite sum, involves Bernoulli numbers. And if you take m, and if you replace m by 2m plus 1 and let alpha beta equal to pi in second main theorem, then we have this formula. Oh, sorry, I repeated this formula. Okay. No. Yeah, if you take in our main theorem, if you take replace m by 2m plus 1 and alpha beta equal to pi in main theorem, we obtained this. And if you take p tends to infinity here, you obtain this formula. And as a special case p tends to 0, we have for m as a positive integer, for positive integer zeta 4m plus 3 minus this series is equivalent to this Bernoulli sum, finite Bernoulli sum with multiplication with power of pi. And for from here, if you put m equal to 0, you will have a new representation for zeta of 3, which is given by this. And for similarly for m equal to 1, you have a representation for zeta of 7. Now I'll conclude my presentation by some remarks that we just scratched the tip of the iceberg by studying the Koshligov theory of zeta function, which was not present to the mathematical community for about 60 to 70 years. And there are very fundamental questions arises from this theory, that what will be the location of non-trivial zeros, where they lie, is there exist any non-trivial zero? So Koshligov has shown that for positive real number, the non-trivial zero of zeta p of s and eta p of s lie at negative even integers. And he also obtained an explicit analogous Euler's formula only for zeta p of s at positive even integers, which is given by this, and p2k of p is a generalized Bernoulli polynomial. And with the help of this function relation, he evaluated that zeta p at negative odd arguments has the closed form in terms of generalized Bernoulli numbers. However, there is no mention about the zeta p of zeta p of at negative odd integers, and hence also no, he also not discussed about and didn't give any formula for zeta p of 2k in his work. So it will be really interesting to find such a closed form for these two expressions. On the other hand, we are able to obtain the analogous formula for zeta p of 2k plus 1, but not for eta p of 2k plus 1. So it also be interesting to see the formula, to obtain the formula for zeta p of 2k plus 1. And the main question was What about the non-trivial zeros of zeta p and eta p of s? So this is the current work which I am working with Professor Dixit. And now, as a corollary, if you combine p tends to infinity and p tends to 0 case of first main theorem, we get the following representation. We get the following modular relation, and from here, if you take alpha equal to 2, we obtain a very two strange inequalities involving digamma function, which are given by this summation n goes to infinity 2 psi 4n plus psi of n, and this term is less than or equal to this quantity, and similarly we have another inequality. So with this,
You should show what that transformation is and how do you get these inequalities from there. You can explain.
Yeah, so actually you can see if you put alpha equal to 2 here, so this is nothing but cos square of t by 2 log 2 upon 1 plus t square, which is a positive quantity, and this is also a positive quantity, and this is also positive. So the right hand side is completely the positive quantity. So from here it's easy to see that both the sides are less than or equal to 0, greater than or equal to greater than 0. So from there we obtain these inequalities. Yeah, so with this I'll end my talk, and thank you for listening. Thank you.
Very nice talk. I think
you,
Professor Ajit Iqbal Singh had some questions in the middle. Now. Then we can
let me see.
You see, you had this sequence lambda j,
Yeah.
and then you later used e raised to beta j. You know, so let me put mu j equal to e raised to beta j. That means jth power of e raised to beta. Now, when you take the number 2, then you see sigma 1 by 2 raised to n, that becomes binary sequence, and it is an interval filling sequence in the sense that all sub-series, when you take sums of all sub-series, that is the interval 0 to 1. So such intervals, such sequences are called interval filling sequences. And if you take 1 by 3 raised to j, that will not fill interval. So in terms of exponentials, it is not interval filling because e raised to beta will be bigger than 2. But when you have q between 1 and 2, then 1 by q raised to j is interval filling sequence. And there is a lot of literature on that, and it was started by Kakeya, and there is a paper by Ribbenbaum, Paula Ribbenbaum, in 1985 and Sinemente on such sequences also, and relating it to Fibonacci numbers also. And then there is a lot of literature on lacunary series, like there is Hadamard condition, nj plus 1 over nj, infimum of that is bigger than or equal to 3. That means gap is big. So what happens when you take such lacunary series or such interval filling sequences in your series sums? That was my question. I mean, I'm not wanting you to answer right now.
Yeah.
I'm politely putting it that you can consider it. You know?
Yeah, sure. It will be great if you can see this problem. Yeah. Thank you.
Thank you. And
if I get any solution, I'll let you know.
Yeah, so there is a lot of work on Kakeya's problem. You know, by Katov, they don't refer to Kakeya, but Ribbenbaum refers to Kakeya. And there is a paper by me and my student, Laltan Puya, in journal Convex Analysis, where we consider these interval filling sequences and give all the references. That is in 2008. So it will be an easy way to trace back the literature.
Yeah, it will be great to go over that literature. We'll definitely go over that.
I can even forward you my talk in which I introduce these things informally.
Yeah, that will be quick and great. Yeah, you can forward it.
So you can either send you my mail or I can send it to Atul.
Okay. So should I write my email address in the chat? So you can pick it.
Okay. Or you note my email, ajitis@gmail.com.
Okay.
Ajit is my first name, IS coming from Iqbal Singh. And then gmail.com.
Sure. I'll keep in mind.
So then I will send you my old talk that I gave at George Washington University and such sequences.
Sure.
And it is very good talk, very good, you know.
No. It will be.
Thank you.
Okay, any other questions or comments?
Yeah, I think there are some questions. Yeah, yeah.
No, sorry, Rajat. I was the great talk actually. Of course,
Thank you.
put a lot of details, so I would love to go over this. You have probably uploaded it, or maybe you will do it in a few days.
Yeah. This paper?
The paper, yes,
Yeah, yeah. It actually in the archive.
it's in archive, so I will
Yeah.
read it. But the
Sure,
main thing is definitely what Professor Rajit Iqbal Singh was asking was something in my mind also. Like lambda j is
Mm-hmm.
generally you have already said when p tends to 0, it's like j minus half or
J minus
something.
half.
Already
Yes.
lacunary, like what she was saying. But
Mm-hmm.
what about in the general case? Like you have some lower bound on the gap minimum.
Yeah.
I think that's
Yeah. So if you plot a curve, like you have this relation,
Mhm.
let me go over that.
Yes.
So it may be easy from there if I can explain.
Yes.
Can I say something more?
Yeah, yeah, please.
Yes, ma'am.
You
Go
know,
ahead.
this alpha beta equal to 1 condition comes up in uncertainty principles, like Hardy theorem, where, you know, function and its Fourier transform. There is a lower bound on the integrals, you know. It comes
Okay.
in Hardy's theorem, and there the condition is exactly alpha beta equal to 1, what happens? Alpha beta bigger than 1, what happens? Alpha beta less than 1, what happens?
Mm.
So they are coming under Hardy's theorem. There is a
Okay.
lot of literature under Hardy's theorem
Mm-hmm.
and uncertainty principles.
Okay. Sure. So let me go over this. Yes. So as I said, so these are the increasing sequence in the positive. It has a positive real roots and it has an increasing sequence of solutions. So if you plot a curve, like if you take like 10 pi lambda minus lambda upon p. So if you plot a curve, you will see that those lambda j's are actually nothing but in between j minus half and j. So from there, we can conclude that p tends to infinity, it goes to j, and for p tends to infinity, it goes to j minus half. In between, for any particular p, we don't know, we yet don't know about anything about the
Anyway, the
location.
lower bound would be half. So you're saying
Yeah.
that gap would
Yeah,
be
lower
minimum.
bound was j minus half.
That
for every j.
definitely you have as an answer. I mean,
Yeah.
anyway, I've forgotten my other questions. I'll ask you later. I will
Sure,
read
sure.
your archive paper.
Sure,
But
sure.
thanks. It was a nice one.
Mm-hmm. There was some question in chat also I read, but I'm not able to find.
Any other questions? Okay, I wanted to ask you, I mean, have you considered Q analogs of zeta p? I mean,
Not yet. Not yet. No, no.
you think there is some related theory there because you know essentially you have defined something p analogs of all lot of interesting functions, right, which are all connected with each other.
Yeah.
And there are q analogs of such things as well as elliptic analogs of such things, which are coming up which are being studied these days in physics and all that. I mean, the elliptic gamma functions really gonna follow.
Yeah, it will be interesting to see the Q analogs of those.
So have you considered any of that? I mean, you think that
No, not yet. Not yet.
So this zeta sub q of s, the q analog of zeta function is related to these Eisenstein type series, right? N to the s q to the n upon 1 minus q to the n, summation n equal to 1 to infinity.
But it's not, somehow it's not related to the q analog of the gamma function, is it? I mean, the relationships are not as good as the hypergeometric case or the q equal to 1 case. But
Right.
so I wonder if in this theory the relationships are good or not.
Okay.
I mean, one could define q analogs of zeta function, but you never see them anywhere. You see a lot of q analog of the gamma function, right, all over the place, but you don't see the zeta function and integrals. And you know, I mean, these integrals look very much like something which even Ramanujan has q analogs of such things. And these series are, I mean, this series is not anything different.
Actually, one thing like coming into my mind about the Q analog of Riemann-Zeta function, I think Robert Snyder actually considered that Riemann-Zeta of Q analog of Riemann-Zeta function by introducing Q brackets. I'm not.
I mean,
if I'm not-
even as in the case of just those series summation n to the s q to the n 1 minus q to the n, Zudulin has done some work. So
Oh, yeah.
uh,
Yeah, but in this case, yeah, it will be interesting to see.
yeah, it was actually somewhat difficult for us to choose what all to pick and then submit, because he was also completing his thesis. So
Yeah.
what topics to really choose to put in the first paper of this on this. So
Yeah, I mean, it looks like you have dug quite a nice gold mine, and that's the perfect thesis problem. It's very interesting. And also a comment on Atul that, you've taken Rajat's grandfather's lead in digging up original historical, pushing that work. So that's very nice. So it's a long family tradition. I suppose. Very nice. Okay, any further comments or queries? Okay, so can we unmute and thank the speaker? It's a very nice talk. Thank you very much, Rajat. Good job.
Thank you, sir. So should I stop sharing the